at the bending line terminal loads. So last time we made certain assumptions about the stress field. So let me just write down those assumptions here. So this is tau xx is equal to tau yy is equal to tau xy is equal to 0, and tau zz is equal to minus e times L minus z times kappa x times x plus kappa y times y. And so these constants kappa x and kappa y are to be determined. And of course tau xz and tau yz are also non-zero. So del dot tau equal to 0 will reduce to del tau xz by del z is equal to 0. Then del tau yz by del z is equal to 0, and del tau xz by del x plus del tau yz by del y plus e times kappa x times x plus kappa y times y is equal to 0. So this is the z component of the equation del dot tau is equal to 0 here. And the lateral surfaces are traction free. So we will get that Tx is equal to Ty equal to 0 on C. So Tx is equal to Ty equal to 0 on C. That is this contour here. And so that can be expressed in terms of the stresses as tau xz times nx plus tau yz times ny equal to 0 on C. So this is the boundary condition that we have on this particular surface here. Okay, so now let us try to find an expression for this Wx. So remember that there is a traction distribution on this surface here, and then the resultant of that traction distribution is this load Wx. Similarly, the traction distribution gives a resultant in the y direction of Wy. So if I now write the expression for Wx, so that is equal to integral of tau xz times d. Right? So that is just actually Tx on that particular surface, and Tx on that particular surface is tau xz dA. So that is equal to integral of tau xz plus x times del tau xz by del x plus del tau yz by del y plus e times kappa x times x plus kappa y times y, the whole thing times dA over A. So here what we have done is that we have added this equilibrium equation. So this is let's call this as 1, let's call this as 2, let's call this as 3. So this is by 3. So basically what we are doing is that we are just adding a 0, because this whole term is 0. So we are just adding x times 0 here. So this is being done because that will help us to simplify, get an expression for this Wx, as we will see. So some of these tricks are very similar to the tricks that we use in the torsion part here. So now I can write this as del by del x of x times tau xz plus del by del y of x times tau yz plus this is the whole thing times dA plus integral of e times x times kappa x times x plus kappa y times dk over a. And then now we can apply the divergence theorem to this. So this is of the form del dot some vector a, where a is equal to x times tau xz and x times tau yz. Okay, so we can apply. So this becomes a dot n. So this term can be now written as follows. So we can write this term here as equal to. So this is integral over c of x times tau xz times nx plus tau yz times ny times ds plus integral of e times x times kappa x times x plus kappa y times times dx. And so now by the traction free boundary condition, tau xz nx plus tau yz ny is equal to 0. So that is this particular condition here. So this part goes to 0. And then this part can be now simplified. So this is equal to e times kappa x times I y minus e times kappa y times I xy. Okay, so simplify this particular expression and use the fact that I y is integral of x square dA and Ixy is minus of integral of xy dA, then you will get this particular expression here. Similarly, now we can find an expression for Wy also. So then that results in a similar expression here. So you will get that Wy now is equal to integral of tau yz times dA over a. So this is equal to integral of tau yz. Again, we use a similar trick. That means we add a 0 here. So this is y times now del tau xz by del x plus del tau yz by del y plus e times kappa x times x plus kappa y times y, the whole thing times dA. And then similar to this, you carry out a simplification. And what you will get is that this is equal to minus e times kappa x times I xy plus e times kappa y times I xx. So basically now we have two equations. So this is the expression for wx. So let us call this equation as 1. Let us call this equation as 2. So we have two equations for the two unknowns kappa x and kappa y. And so we can solve for this kappa x and kappa y. And then we will get the following expression here. So you will get now that kappa x is equal to Ixx times wx plus Ixy times wy divided by e times Ixx Iyy minus Ixy squared, and kappa y is equal to Ixy times wx plus Iyy times wy divided by e times Ixx Iyy minus Ixy squared. So we have now managed to solve for the tau zz, because now see wx is known, wy is known, hence kappa x, kappa y are known, and then the tau zz is known. So now the only fields that are still not found are tau xz and tau yz. Those are the two things that we have still not found out here. Okay, then what about the Ez? Okay, so that the force on this particular face in this z direction that should be equal to 0 here. So, so let us find that. So Fz is equal to integral of Tz dA. This is over A. So this is equal to integral of tau Zz now times dA. So that is equal to E times Z minus L times kappa x times integral of x dA plus E times Z minus L times kappa y times integral of y dA. And see, now these are centroidal axes, right? So we have said that this axis runs through the line of centroids, and hence integral of x dA and integral of y dA is equal to 0 because that is a centroidal axis. So so this basically becomes equal to 0 because so that shows that the force in the z direction is 0, and that is what we require, right? So that is the requirement of this one. Similarly, the resultant moments are mx is equal to integral of y times tau zz times dA, and this, if you integrate this, you will get that you will get minus w y times L minus z, and similarly you will get my is equal to minus of integral of tau xz dA, and that is equal to wx times L minus z. So if you draw a free body diagram, right? So suppose if you draw a free body diagram, and this is z, this is L minus z, and then you will see that these are the moments that are generated due to the loads wx and wy. So even this part, the moments also agrees with whatever is expected here. So as I said, now the stress field tau zz is now completely determined, and we now have to determine tau xz and tau yz, right? So let us now try to find tau xz and tau yz from the remaining equations that we have. Okay, so we can write now tau xz and tau yz in terms of a stress function phi of x comma y. See, we know that del tau xz by del z is 0, del tau yz by del z is also 0. So this stress function can be taken only as a function of x and y here. So tau xz we can write as del phi by del y plus f of y minus half of e kappa x times x squared, and tau yz is equal to minus del phi by del x minus g of x minus half of e kappa y times y squared. So now these functions f of y and g of x, these are introduced in order to simplify the boundary conditions. Okay, so that we will see at a later stage. So actually, see, because the phi is an unknown, we need not have introduced this f of y and g of x because they can be absorbed in the function phi. But as I said, that these are kept separate so as to simplify the boundary condition at a later stage. So right now let us just keep these functions here. Now you will see that this will automatically satisfy the equilibrium equation. Right? Automatically satisfies del dot tau equal to 0. So at the beginning of the class I wrote the equations del dot tau equal to 0. So you will see that if you substitute these expressions for tau xz and tau yz in that del dot tau equal to 0, you will see that they are automatically satisfied. Now the one thing that we have to ensure is compatibility, because we have guessed the stress field. So in order to ensure a single valued displacement field, we need to ensure compatibility, right? So if we had started from the displacements, then we need not have checked for compatibility, but now because we are guessing the stress expressions, hence we need to check for compatibility here. So first let us find out what are the strain components corresponding to this particular stress field. So you will get that epsilon xx is equal to epsilon yy is equal to minus mu divided by E times tau zz. And epsilon zz is equal to 1 by E times tau zz. So this is from the constitutive relation. So these are the relations that you will get. Then gamma xz is equal to 1 by G of tau xz. Gamma yz is equal to 1 by G of tau yz. So these are the expressions for the strains. And now if you substitute it into the 6 compatibility relations, so the only 2 non-zero compatibility relations, so substitute into compatibility. So compatibility leads to del square by del of del square phi by del x is equal to minus 2g mu times kappa y minus d square g by dx square. And the other equation that we will get here. So the other equation is del by del y of del square phi is equal to minus 2g mu kappa x minus d square f by dy square. And so if you integrate these two compatibility relations, then what you will get is del square phi is equal to minus 2g mu times kappa y times x minus dg by dx plus 2g mu times kappa x times y minus df by dy minus 2g alpha. Okay, so this 2g alpha here is like an integration constant. Constant, because see when you are integrating this, you need an integration constant, and so that is an integration constant. You can easily verify that if you now differentiate this expression with respect to x, you will get the right hand side, and if you differentiate this expression with respect to y, you will get the right hand side of this particular equation here. Fine. So how do we determine now this alpha? Okay, so that is something that we will discuss at a later stage. So basically this alpha will represent the twisting of the cross section. Okay, so you can imagine that suppose if you imagine that there is a cross section of this particular kind here, and this is x and this is y. Now if your load, resultant load is not passing through the axis of symmetry, right, then you can imagine that this cross section is going to twist like this, right, because you are applying the load which is away from the symmetry axis, and then this alpha will represent the angle of twist of this particular cross section. Okay, so that is something that we will discuss at a later stage, but I am just trying to give you the physical interpretation of this term alpha here. Fine. Now let us look at the boundary condition now. So this is the governing equation for phi. Now we need a boundary condition for phi, right? And so this is the governing equation. Now we will derive the boundary condition for phi. So that is obtained from the traction-free boundary condition. So you will get that. So from the expression that tau xz times nx plus this. This is the traction-free boundary condition. So tau xz nx plus tau yz and y is equal to 0. So this will give me, if you substitute, so we will get del phi by del y times dy by ds So I am again using the usual expressions for nx and ny here. So nx and y is equal to dy by ds and minus dx by ds. So that those are the usual expressions for the normal, and so this is plus del phi by del x times dx by ds. So that is equal to d phi by ds basically. So d phi by ds, and so this is equal to half of e kappa x times x squared minus f of y times dy by ds minus half of e kappa y times y squared plus g of x times dx by ds. So this is the expression that we now have here. And then, so basically the idea is that we will choose these functions f of y and g of x in such a manner that it will simplify the boundary conditions here. But at this particular stage, you can see that phi is a function of s. So s is the parameter. That parameter is the boundary c, and so this d phi by ds is a function of s in general. So as I said, that in some cases we may be able to simplify this. So let us try to see how to carry out that simplification. But before that, we still need to figure out whether this problem is well posed. Okay, so phi is a single valued function of s, right? And so integral of d phi by ds times ds should be equal to 0, right? Because it's a single valued function. So basically, if you start from this particular point and you go around the contour and you come back to the same point, then the integral of that will be equal to 0, right? So that ensures the single valuedness of phi. So now we have to verify whether the d phi by ds that we have here satisfies this particular equation. Let us look at that. So we get that half of e kappa x times x squared minus f of y times dy by ds minus half of e kappa y times y squared plus g of x times dx by ds, the whole thing times ds. Okay, so this is now your integral of d phi by ds, and so we want to show now that this is 0. So if it is 0, then the problem is well posed. So this is equal to integral over c of half of e kappa x times x squared minus f of y times an x plus half of e kappa y times y squared plus g of x times ny times ds. And so this is equal to integral of e times kappa x times x plus kappa y times y times dx. So this is obtained by using the divergence theorem here. So this is basically divergence theorem. And so that is just you are transforming basically this will become del by del x of this particular term plus del by del y of this particular term, and then this is what you will get. So this is over area A, and that is equal to 0 because the z-axis is the line of centroids, and so integral of x dA is equal to integral of y dA is equal to 0. So this is because since integral of x dA over A is equal to integral of y dA over A is equal to 0. So because of this. So basically now we can say that this problem is well posed because we have ensured that integral of d phi by ds over the contour C is equal to 0. Okay, so now as I said that let us turn to the task of finding this g of x and f of y. So the idea here is that this for certain types of cross sections we can choose this g of x and f of y such that the boundary condition that d phi by ds becomes 0. Okay, so that's so let us look at that particular simplification now. So for certain types of cross sections, and certain types of loading and types of loading, the g of x and f of y can be chosen such that half of e kappa x times x squared minus f of y times dy by ds is equal to 0 on C, and half of e kappa y times y squared plus g of x times dx by ds is equal to 0 on C. So we can choose. So remember that this is only on the boundary that we are talking about. Okay, so on the boundary we can choose the f of y and the g of x such that this whole thing is equal to 0. Okay, and similarly this term is also equal to 0. So from this, because these two are now 0, this will imply that d phi by ds is equal to 0 on C, and so that will imply that phi is equal to a constant on C. And so we can take this phi to be 0 because if you look at the expressions for the stresses, they involve derivatives of the phi, right? And so the constant is not going to make any difference. So we can just take it to be 0. Right? So this so since stresses are derivatives of phi, so hence can take this constant to be 0. Take constant to be equal to 0. So basically what we will do is that so this will imply that phi equal to 0 on C. But remember, so one very important thing to remember here is that this is very important. So only for certain types of cross sections and loading can we take this. So it is not that for all cross sections and all geometries we can make this assumption. So we will look at certain problems where we can make this particular assumption here. So one thing to note here is that suppose if dy by ds is equal to 0 on part of the boundary, right? Then actually the f of y can be chosen arbitrarily, because so then we need not have this term to be 0 because only the product of this needs to be 0. So let me give an example. So suppose now if you have a rectangular cross section, then along this particular edge your y is the x is a constant, right? So suppose let me just draw this. So this is x and this is y. So this is y equal to a constant, correct? And then because y is a constant on this particular edge, your dy by ds will be equal to 0 on this particular edge. So on this particular edge, this f of y can be chosen arbitrarily. But suppose now we are looking at this particular edge, right? Then on that edge, your dy by ds is not equal to 0. Then you would need that this half of e kappa x squared minus f of y should be 0 on this particular boundary here. So as a combination, so as a product it should be 0. So individually they need not be 0. So that is the important thing to remember in this particular case here. Fine. Okay. So now, what about that alpha, that constant, the integration constant? So we have still not talked about that particular thing. So that constant is now obtained by looking at the moment equation about the origin. Okay. So you can see that the moment is going to be given by x naught times w of y minus y naught times w of x. So that moment should be equal to integral of x tau by z minus y times tau xz. And so from that we will be able to get an expression for the alpha. Okay. So let us now talk about this determination of that alpha, the parameter. Okay, so let us, so this is now, we are talking about the determination of alpha. So this is that integration constant, right? Integration constant in equation for phi. Right? So let us try to see this. So we will use the moment equation, so that is x naught times wy minus y naught times wx is equal to integral of x times tau by z minus y times tau xz times dA or a. So that is the usual expression for the torque, basically, about the z-axis. Now we will use some manipulations in order to try and simplify this particular expression. So first we will substitute for tau xz and tau yz in this expression and see what we get. So let me just write it here. So this is a, and this is x times minus del phi by del x plus minus of g of x minus half of e kappa y times y squared. So this is yes, and minus y times del phi by del y plus f of y minus half of e kappa x times x squared times the whole thing times b. This is the whole thing times dA. And let us now simplify this. So again we use some tricks in order to simplify this. So we will get that this is 2 times phi minus e kappa x times x squared y plus e times kappa y times xy squared times dA plus integral of a del by del x of minus xp minus xy f of y plus half of plus half of e times kappa x times x cubed y minus integral of minus del by del y of y times phi plus xy g of x plus half of e kappa y times xy cubed, the whole thing times the dA. So this is the so basically we are just rearranging certain terms so as to get this. So this is some manipulation that we are doing in order to get a simplified expression for this whole thing here. And now this is equal to 2 times phi minus e times kappa x times x squared y plus e times kappa y times xy squared times dA over a plus integral of minus of x phi minus xy f of y plus half of e kappa x times x cube y times dy by ds. So basically we are applying the divergence theorem now again. So this is C plus integral of y phi plus xy g of x plus half of e kappa y times xy cube times dx by ds times ds. Okay, so this is all. These are all contour integrals here, and so then what we will get on simplifying these particular expressions is that this is equal to now integral of 2 phi minus e kappa x times x square y plus e times kappa y times xy square, the whole thing times d. So that is because you can see that this is equal to 0 by the traction free boundary condition, right? That integral of tau xz times nx plus tau yz times ny equal to 0. So from that we will get that this whole contour integral, whatever we have, is equal to 0. And so, so let me just write that down here. So that is because we had that. So let me just write that here. So if you recall, we had said that half of e kappa x times x square minus f of y times dy by ds is equal to 0, and also half of e kappa y times y square plus g of x times dx by ds is equal to 0. So from these two equations, you will see that this whole thing goes to 0. So that is, as we said, that for certain types of cross sections and certain types of loadings, we can assume these two equations. And so we are now assuming these two equations, then this whole thing goes to 0, and then we have this simplified expression that you will get for the tau. And so this 2g alpha is now determined from this particular equation here. So the 2g alpha is determined using this equation now. So basically now let us summarize the whole thing. So we got an equation for del square phi, right, which involved this 2g alpha, and so that is the governing equation for phi. Then phi equal to 0 is the boundary condition on C, provided we can find the f of y and the g of x for that given particular cross section that satisfy these equations. And that integration constant 2g alpha is found from this particular equation here. So that way we can solve now for the entire function phi, and once you know the function phi, then you can find out what are the stresses tau xz and tau yz. Okay. So that is the procedure. So we will illustrate this procedure on certain types of cross sections, such as the elliptical cross section or the rectangular cross section at a later stage. But at this stage, let us just continue this particular discussion. So now let us try to give a physical interpretation for alpha. So I already mentioned, right, when I showed you this particular example, we showed that this alpha will represent the twisting of that particular cross section. So let us try to give a justification for why this alpha represents the twisting of that particular cross section here. So let us do that now. Okay, so as I said that this this del u minus del u transpose and hence omega, which is equal to del cross u, which is the axial vector of this one, which is the axial vector of this del u minus del u transpose is a measure of rigid rotation. Is a measure of rigid rotation undergone by an element. So this is very similar to your vorticity, right? That omega is del cross u. So here actually u represents the displacement. In that case, in the case of fluid mechanics, it represents the velocity. And so the vorticity, just like the vorticity is a measure of the rigid rotation of an element, so in the same way, this del cross u is a measure of the rigid rotation that is undergone by a particular element here. So here we are interested in this omega z now, because we are interested in the rotation of this particular cross section. So that will represent omega z, correct? So that the z component of that. So omega z will be equal to half of del u y by del x minus del u x by del y. So so this is a measure of the rigid rotation, measure of a rigid rotation, undergone by an element, in the xy plane, in the xy plane here. And so we will define a local twist now. So define a local twist, which is del omega z by del z. So that is equal to half of del square u y by del x del z minus del square u x by del y del z. So just basically differentiate this with respect to z, then this is the expression that you will get. And if you express this in terms of the strain components, so you will get that this is del gamma yz by del x minus del gamma xz by del y. And in terms of the stresses, now this will become 1 by 2g of del tau yz by del x minus del tau xz by del y. And so this represents a measure of the twisting of the cross section. So let us see why this represents a measure of twisting of the cross section. So let us take the example of torsion. Correct? So in the case of torsion, so for the case of pure torsion, we have that del omega z by del z is equal to, so if you substitute for tau yz and tau xz in terms of the Prandtl stress function, so this is minus del square phi by 2g, and this is equal to, so in this case this is the Prandtl stress function, and what you will get is that so in the case of torsion we know that del square phi is minus 2g alpha, so there we will get that del omega z by del z is alpha. So that is basically the twist correct? The alpha there is the angle of twist per unit length, and so we can see that this del omega z by del z is a reliable measure of twisting here. So this shows, shows that del omega z by del z is a reliable measure of twist. Is a reliable measure of twist of the twisting of the cross section here. And so now let us apply this measure to the problem at hand now and see what we get here. So applying it to the current problem now. So this was, so what I have done here is that I have applied this measure to the case of pure torsion. Now let us apply it to the case of this bending by terminal torque. So applying this measure to the problem at hand now. The problem at hand. What we'll get is that del omega z by del z is equal to minus 1 by 2g times. So I'm just substituting for the expressions for tau xz and tau yz in that expression that I have derived. Then you will get del square phi plus, this is del square phi plus dg by dx plus df by dy. And so if you simplify this, so substitute for del square phi, then you will get minus 1 by 2g times minus 2g mu times kappa yx plus 2g mu kappa x times y minus 2g alpha. And if you simplify this further, you will get alpha plus mu times kappa y x minus kappa x times y. So for the problem at hand, now this is the twist that you get, and now you can see that the mean angle now, so mean angle of twist, twist, so that is equal to integral of del omega z by del z times dA over integral of dA will be equal to alpha, because the integral of x dA and integral of y dA is equal to 0. Right? So since integral of x dA is equal to integral of y dA is equal to 0, because the z axis is the line of centroids here. Or alternatively, you can think about it that alternatively the del omega z by del z evaluated at x equal to y equal to 0, is equal to alpha. So we can give the interpretation as follows, that basically it is either the mean angle of twist of the entire cross section. So that means that this is the example that I have given, that this cross section basically will twist if your load is not passing through the symmetry axis, right? So so what is this angle of twist? So that is given by this particular thing, that this alpha will represent this either the mean angle of twist of the entire cross section or the angle of twist at the origin. So either interpretation is fine. So basically, let us just conclude this discussion here that thus there is twisting, and this twisting is given by this alpha. So there is a twisting in addition to bending. In addition to bending of the cross. So of course, bending means it is just bending down in this particular direction here, and also there is a twist of this particular cross section. So if the load doesn't pass through the symmetry axis in this particular example here, so we will look at this so this is basically the concept of shear center. Some of you may be familiar with this concept of shear center. So we will introduce. So basically, if the load does not pass through this point, which is called as the shear center or the center of flexure, then there will be twisting. If it passes through the shear center, then there is no twisting. Okay, so this is something that we will discuss in the next class.